There is a story circulating about a massive data center project in Utah that has captured the attention of energy regulators and tech analysts alike. The claim is staggering. It suggests that this single facility is expected to generate and consume more power than the entire state currently uses. While the exact numbers on the Utah project remain a subject of intense debate and verification, the underlying premise touches on a truth that is becoming undeniable across the entire industry. We are facing a moment where the demand for artificial intelligence is colliding directly with the physical limits of our electrical infrastructure. This is not just a story about where servers are being built. It is a story about the fundamental trade-off between energy and compute and how that balance is reshaping the future of technology. To understand the gravity of this situation, we need to look past the hype about faster chips and smarter algorithms. We have to look at the grid itself. Think of the electrical grid like a massive highway system. For decades, we have been adding more cars to the road, but the road capacity has not kept pace with the traffic. Now, imagine that instead of regular cars, we are introducing heavy trucks that consume fuel at a rate that dwarfs everything else on the road. That is what happens when you deploy hyperscale data centers for artificial intelligence. These are not your standard office buildings or cloud storage facilities. They are essentially power plants in reverse, sucking energy from the grid to run thousands of servers that are working at maximum capacity. The specific challenge with artificial intelligence workloads is that they are not steady. They are dynamic. A traditional server farm might run at a relatively constant load, but AI training and inference involve rapid load transients. This means the power demand can spike and drop in milliseconds. Imagine a power grid like a giant flywheel that needs to spin at a constant speed to stay stable. If you suddenly add a massive load, the flywheel slows down. If you remove it too fast, it speeds up. These fluctuations can destabilize the frequency of the electrical network, potentially causing brownouts or even blackouts in surrounding areas. This is why researchers are emphasizing that AI workloads pose significant challenges to grid stability and power electronics infrastructure. It is not just about having enough total energy, it is about having energy that is stable enough to support the grid. This creates a critical feasibility paradox for projects like the one in Utah. If a facility is proposed to consume more power than the state generates, it implies a systemic gap between AI infrastructure planning and grid constraints. We are seeing a situation where the rapid approval trajectory suggests a strategic prioritization of artificial intelligence infrastructure development over immediate grid modernization. In many cases, this sets a precedent for other regions to face similar supply-demand mismatches. The question becomes whether we can build the power generation capacity fast enough to keep the computers running, or if the computers will have to slow down because the power is unavailable. There is also a national dimension to this problem. Feasibility studies suggest that United States hosting capacity is limited to tens of gigawatts due to land and grid adjacency limits. This means that even if we have the money and the desire to build more data centers, the physical reality of connecting them to the grid is a bottleneck. You cannot just build a data center anywhere. It needs to be adjacent to power sources that can handle the load without collapsing the local frequency. This forces a shift in how we think about location. It is no longer just about land cost or labor availability. It is about electrical availability. So, how do we solve this? The consensus among experts is that future hyperscale development requires coordinated solutions between operators and developers to manage these constraints. But there is a more profound shift that is beginning to happen. Future deployments will likely require a fundamental change from passive consumption to active grid participation. Currently, data centers are seen as loads that must be served. In the future, they may need to act as stabilizers. This involves leveraging data center load flexibility for frequency regulation to stabilize an increasingly strained electrical network. Consider this analogy. Imagine a group of people standing on a seesaw. If everyone stays still, the seesaw stays balanced. But if everyone starts jumping up and down at the same time, the seesaw becomes chaotic. A traditional data center is just one person jumping. A smart data center can coordinate its jumps with the others to keep the board level. By adjusting their power consumption in response to grid signals, these facilities can help maintain the frequency stability that the grid requires. This requires new regulatory frameworks and on-site generation solutions to achieve operational viability. It means that the data center becomes part of the power solution, not just the power problem. This represents a tipping point where the energy intensity of hyperscale computing outpaces traditional utility expansion. We are entering an era where the energy intensity of artificial intelligence outpaces traditional utility expansion. This necessitates a new way of thinking about infrastructure. We cannot simply assume that the grid will magically expand to meet the demand. We have to engineer the demand to fit the grid. This involves complex coordination between the facilities and the utility providers. It involves designing systems that can ramp up and down without destabilizing the network. It involves investing in on-site generation that can provide baseload power for energy-intensive artificial intelligence workloads. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.